Hello dear students. So, in continuation with our earlier discussions, so far we have seen, we have considered plasma a collection of charged particles as a single particle. So, we were dealing with the particle description of plasma. So, like I said, plasma can be dealt with in three different ways, which are particle description of plasma, statistical description of plasma. And so, what differs in these descriptions is that the way we treat plasma is basically different. So, what we do is in today's class, we will continue a discussion of single particle movement or motion in various different types of fields. So, to begin with, we have considered plasma movement in an isolated homogeneous static electric field, and then we have seen isolated homogeneous static magnetic field. We have seen that we have considered the field to be in a particular direction, and we have considered a particle such as electron or ion to be experiencing these different types of fields. What we realized is that in both these pictures, the net amount of work done, that is change in the kinetic energy or change in the total energy, was maintained to be 0. This is what we have noticed. And in addition to this, what we have seen is that if the particle is entering an electric field, an isolated electric field, we have realized that it will accelerate along the direction of electric field, and this acceleration of this velocity linearly increasing with time will lead towards charge separation of both the charges, and which will conserve the total energy. And when we considered only the magnetic field, we have seen that the particle will gyrate along the direction of, let us say, will gyrate like this, and this direction of this gyration was also called as Larmore's precession, right. Then we have realized that different types of particles, let us say ions and electrons, will gyrate in opposite directions, and we have also seen that the net amount of work done in this picture will be 0, that is change in the energy is 0. Okay. Now, so this was one example that we have seen. So, in today's class, in continuation to this discussion, what we will do is we will consider perpendicular electric and magnetic fields. So, we will consider an example in which there is an electric field and there is also a magnetic field such that they are perpendicular to each other, and you allow a single particle to experience this type of field. Okay. So, if we allow a non-zero electric field to be present along with the magnetic field to our earlier description, the motion of the particle will be a combination of motion of the particle in the presence of an electric field and motion of a particle in the presence of a magnetic field. Now, so the particles, let us say particles are two types, let us say depending on their charges. It can be a positively charged particle or it can be a negatively charged particle, and these two particles will have some amount of charge. Let us say any particle will have some amount of charge and will have some amount of mass. Okay. Now, this is subjected to a field arrangement in which E and B are perpendicular to each other, let us say. So, now let us say let us consider the electric field to be present in the x and z plane. Let us consider this is the coordinate system that we consider x, z and y. Now, the magnetic field is present along the z axis and the electric field is present along the x and z plane. So, this is in the x z plane you consider the electric field is present and the magnetic field is present along the z axis. So, the magnetic field is present in the z axis, along the z axis. Okay. Now, when the electric field is present only along the x z plane, we take B to be Bz and E to be existing along x z plane. That means these components of electric field along these directions will be non-zero, and the electric field along y axis, y direction, will be 0. Okay. Now, as you see, the z component of the velocity is unrelated to the transverse component and can be treated separately, right. Then the equation of motion, how do you write the equation of motion? We will write simply the equation of motion as m dv by dt is q times E plus v cross b. What do we have here? So, what we have done so far is that we have dealt with this equation separately. So, once when there was only electric field and once when there was only magnetic field. In both the types of solutions, we have realized that we can write the velocity or we can integrate this velocity to get the position as a function of time. So, in the second case, for example, in the second case when there was only a magnetic field, we have realized the solution of x and y which will satisfy this differential equation resembled something which is circular motion in nature, right. So, now what we are about to do is we are about to combine these two things. That means, we are about to combine the description of a particle in an isolated electric field, static electric field, and the description of a particle in a magnetic field, right. Now, let us see. Now, in order to do that, we will need the solutions of both the pictures. Let us say solution of equations of motion in E as well as B. In both the pictures, we will need the solution. Then we will combine these two solutions in a suitable form, so that we can get the final picture. Okay. Now, let us say that when the field is along only z axis. So, we have considered the field to begin with. I am just recollecting the equations that we have derived in the earlier classes, so that I can use them for combining them. When the electric field or magnetic field was only along the z axis, we have written the equations of motion as m dvx by dt is equals to 0, m dvy by dt is equals to 0, m dvz by dt is equals to q ez. Okay. Then the second set of equations m dvx by dt is equals to q vy b, m dvy by dt is equals to q vx b with a minus, and m dvz by dt is equals to 0, right. So, we will have to combine these two equations for a successful description of the picture. So, the z component of velocity will not be influenced by the magnetic field. Why is it? Let us redraw the figure for our reference. So, we have the coordinate system like this. So, we have z here, x, y, z. So, for our reference, so the magnetic field is in this direction and the electric field is in this plane, right. So, B, z. Now the velocity components are Vx, Vy and Vz. As long as the velocity component is parallel to the magnetic field, it will not be influenced, right. So, when you want to write an equation of motion for the z component of velocity, so obviously, so z component of velocity has to be this plus this. That means, the z component of velocity is simultaneously influenced by the electric field and the magnetic field. Naturally, every component of velocity is influenced by the electric field as well as magnetic field, but here what we have is the particle does have a 3-dimensional velocity, let us say, okay, the particle. So, this can be an electron or ion. So, the particle will have the 3-dimensional components of velocity, but when the magnetic field is parallel to a velocity component, that particular part will be 0. So, here it is. Now, if I write the equation of motion, so the acceleration is only due to the electric field. So, the z component of velocity will change with respect to time only due to the electric field, but not due to the magnetic field. So, if it is the case, I will write, let us say m dvz by dt is equals to q Ez, or let us say you write, for example, m dv by dt is equals to q times E plus v cross b. Let us call this equation as 1, okay. And a component equation of this becomes 2. This is only the z components. So, what does it suggest? It suggests that acceleration is linear with respect to time. So, we can simply integrate this equation to obtain velocity as a function of time. Vz is equals to q by m Ez t plus v z 0, which is just a constant. So, here what we have got is the velocity as a function of time. So, what does it indicate? It indicates that Vz changes linearly with time, and the initial value. So, this is the initial velocity, the velocity at t is equals to 0, right. Now, similarly, similarly we can write the other components of velocity. Similarly, what we can write is d Vx by dt is equals to q by m Ex plus minus q by m Vy b, or Bz, you can simply say Bz, right. Now, what have I done? dVx by dt, let us say dVx by dt is 0 in this picture, in this here, in this it is 0, but if you have an electric field component Ex which is not 0, using this relation similarly you can write m dVx by dt is equals to q by q Ex, which is what I have written. Then in addition to this, the effect of magnetic field also is to be taken into account. So, dVx by dt becomes q by m Vy Bz. So, I have effectively combined, let us say, this equation and this equation, these two equations I have combined. Now, the reason that I have included plus minus is to accommodate ions with a plus and electrons with a minus. Okay. So, this expression I can rewrite as q by m Ex plus minus omega c V y. So, q b by m, where q b by m is omega c, which is the frequency term, which is associated with the Larmor's motion of the particle in the presence of a magnetic field. Okay, let us say this is a very important equation. Let us say this equation is this we are going to call as equation, let us say equation 4. Okay. So, if we do the similar thing across the other direction, let us say Vy. Now, we have already seen that Ex is non-zero, Ez is non-zero, and Ey is 0, right. So, we need not bother about this term. So, this term is 0. Okay. So, the motion of the particle along the y axis is going to be only due to the magnetic field, but not due to the electric field. Okay. So, in that case we can write d Vy by dt is equals to minus plus, because we already have a minus there, q by m Vx b. See, here you already have a minus here in this equation, right. So, the motion of the particle or the rate of change of velocity of the particle along the y axis will just depend on the magnetic field, but electric field it can depend, but we have chosen a field such that the electric field along y axis is 0. we have made a choice like that. So, in that case it is q v x b. So, this is the only term which will contribute for the net acceleration, right. So, this we will rewrite as minus plus omega c v x. So, very important thing that we should notice is that in the acceleration equation of v x, you have the v y term appearing, and the acceleration v x dot has v y and v y dot has v x. Okay. So, this is kind of coupled equations that we have got. Okay. So, now let us say we call this equation as this is equation number 4 and this is equation number 5. Okay. Now, let us differentiate the above equation. Differentiating the equation number 5. Let us say, what do we get? We will write d square v x by dt square is equals to plus minus d v y by dt, right. Now, substitute for d v y by dt from equation 5. What we will get is d square v x by dt square is equals to plus minus omega c times minus plus omega c v x, which will be d square v x by dt square is equals to minus omega c square v x. Let us call this equation as equation number 6. So, we have got a second order differential equation in v x, right. So, we have removed the v y term and we have replaced v y in terms of v x again, right. Now, similarly we can do the same approach for equation number 5 as well, okay, which we can write as d square v y by dt square is equals to minus plus omega c d v x by dt. Now, here we have an additional term, right. So, that means that here the additional term is which comes only from dvx by dt. So, dvx by dt was written to be q by m ex plus minus omega c v y. Using this inside, let us say substituting this into this equation, what we can write is d square v y by dt square is equals to minus plus q by m ex plus minus omega c v y omega c, which will be equivalent to q by m omega c ex plus minus omega c square v y. Taking the we will write omega c square ex by b minus omega c square v y, or simply which will be finally written as d square v y by dt square is minus omega c square times ex by b plus v y. right. This equation, let us call this equation as equation number 7. The equation number 7 can be conveniently written as d square by dt square of Vy plus Ex by B is equals to minus omega c square times Ex by B plus Vy. So, now let us say this, let us call this equation as A. Okay. Now, what have I done by for the sake of convenience? What I have done is, let us say, so we know that the electric field Ex Ez and the magnetic field Bz, they are perpendicular to each other, of course. But what we have taken is that these are homogeneous in nature, or these are static in nature. That means they do not vary with respect to time. So, d by dt of these quantities will be 0. So, taking this advantage, there is no harm in writing d by dt of Ex by B. So, this term is eventually 0, but to get the solution of this differential equation, it becomes easy to have the same multiplier on the left and right hand side. So, if it is the case, so what have I got? I have got one differential equation, one second order differential equation which we called as 6, and the second order differential equation that we have got is called as A, let us say. So, let us, for convenience, or let us say for understanding, let us write these two equations together so that we can understand what do they mean as a whole. So, d square Vx by dt square is equals to minus omega c square Vx is the first equation that we have got, and similarly the second differential equation is d square by dt square of Vy plus Ex by B is equals to minus omega c square into Ex by B plus Vy, right. Now, let us say this is equation A and this is equation B. So, so this is not required. Okay. So, this could have been called by as equation number 8. Okay. Sorry for that. Okay. Now, let us look at these two equations and try to understand what they are trying to convey. So, what is the first thing that you notice about these two equations? The first thing that you notice about these two equations is that they are second order differential equations, and their solution will be, what will be their solution? Their solution will be Vx and Vy with respect to time. So, what is particular about this? What is particular about this is that Vx and Vy will tell you how the velocity of this. So, what happened to Vz? So, in combination with these two, we also have Vz. Vz is omega c q by m Ez times t plus V z naught. So, right. So, this is the second order differential equation, rather this is a solution itself, right. Let us call this equation also for the reference C. Now, what they represent is that Vz is of course changing linearly with respect to time, and when a particle experiences, when let us say an electron or ion which is the part of a plasma experiences a E cross B field. That means, when electric and magnetic fields simultaneously exist, let us say, in such a picture, if the electron or the ion comes across such a field, the velocity Vx, Vy, Vz will behave as shown in equation A, B and C. So, they are not just velocity components which are simply changing linearly with respect to time, but they mean more than that. What they mean more, what I mean is that the velocity components will behave so as to satisfy these three differential equations simultaneously. Okay. Now, these equations A and B can be solved to get Vx as V perpendicular e to the power of I omega c t and Vy as plus minus iota V perpendicular e to the power of I omega c t minus Ex by V. Now, if you see carefully, this term Ex by B has the dimensions of velocity. This has the dimensions of velocity. We know it, I mean, right. So, if you solve these two equations, the solutions of these two equations will be like this, Vx and Vy. Vy is the V perpendicular is the perpendicular component of velocity, V perpendicular is the perpendicular component of velocity, omega c is the Laurent's gyration frequency, t is the time, Ex is the electric field across x axis, B is the field. So, B could have been written by as Bz, so there is no harm in that. Okay. Now, what do these equations represent? So, generally if you want to find out the trajectory, you can simply square it and add it. So, just to find, let us say Vx square plus Vz square, then you will realize what will be the shape of this particular curve. In addition to, so yeah, so this should have been Vy. Now, the most important point what we have to understand here is that Vz, see the particle, let us say in this frame of reference, the particle has a linearly changing velocity component Vz with respect to time along the z axis. Okay. Along the z axis, the velocity is just changing linearly with respect to time, right. You agree, this is a linear. So, this is just y is equals to mx. So, this is a linear changing parameter. Okay. Now, the particle's velocity along Vz depends. So, Vz depends on pretty much on, let us say, depends on charge, depends on mass and depends on the electric field. Now, most importantly, the velocity component along z axis changes linearly with respect to time. You agree, right. But when you look at these two equations, let us call this equation as, let us say, let us rewrite these equations for convenience. It has been, so let us say Vx is equals to V perpendicular e to the power of I omega c t, Vy is equals to plus minus I V perpendicular e to the power of I omega c t minus Ex by V, right. And Vz is equals to q by m Ez times t plus V z0, right. Now, what are we trying to achieve here? We are trying to understand how does the particle move when it has both the electric and magnetic fields. So, this is the field alignment that we have taken, right. So, this is the x axis, this is the y axis and this is the z axis. E along y axis is 0, the magnetic field is along z axis, the electric field is in the xz plane, right. Now, these three equations indicate, so Vz component depends only on Ez, right. So, Vz is changing linearly with respect to time, right. So, inference 1, Vz is changing linearly with respect to time. So, what else you can say about Vx and Vy? So, Vz is changing with respect to time, of course. How about Vx and Vy? So, Vx and Vy, neither of them are linear in time, Vx and Vy, neither. neither of Vx and Vy are linear in time, right. So, they are not changing. So, if you see, you have an exponential term appearing in the beginning, right. Now, what you can realize is that in the first parts, let us say if you expand this and then take a square and add, what you can realize is that Vx and Vy are still the circular motion is preserved in Vx, Vy, is preserved in Vx and Vy. So, in addition to the circular terms, so the circular motion is appearing because of the first terms in Vx and Vy. In addition to the circular motion, you have an additional velocity component which is Ex by B. So, the inference 4 is that an additional term of velocity, which is Ex by B is given in Vy. So, what you can say is that the Vx component of velocity and Vy component of velocity are of course making the particle execute circular motion, but this circular motion is superimposed with another component of velocity which is Ex by B. So, this superimposed component of velocity is generally called as the drift of the guiding centers. Drift of guiding center. Okay. So, this is due to the this drift of guiding center is due to Ex and as well as P. Okay. Now, let us learn more about this drift velocity. Okay. Now, we can say that the Lormor's motion is preserved in a perpendicular E and B field. In addition to this, you have an additional component which you call as the drift of the guiding centers. Okay. Now, let us say to get the more detailed analysis of this study, let us say generally when you have a differential equation as this m dv by dt is equals to q times E plus V cross P. If you have a differential equation like this, you generally write the solution as V is equals to V1 plus V2. Here V1 is called as the particular solution, and V2 is the complementary solution. Or homogeneous solution, things like that. Okay. Now, what you will realize is that when you solve it, V1 will be a function of time, and at the same time V2 will be a constant. V2 will just be a constant. How do you get V2? Let us say, so here also you can see what I am trying to say is that, see this solution, this is the solution of this particular differential equation, right, the Lorentz equation, where you have the charge and mass appearing on the right hand side. So, this you see this, what you see is, you see these two parts, I have already underlined them. So, you have to understand. So, this part is the particular solution and this part is the complementary solution. As you see, the particular solution is very much dependent on the time, and the constant or the complementary solution is time independent. Now, generally if you have a differential equation as this, what is the standard method for you to obtain the complementary solution? The complementary solution is simply obtained by equating it to 0. That means by equating the RHS to 0, that is it. So, you can write, so now since we are dealing with only V2, m dV2 by dt is equals to 0, right. That implies q times E plus V cross P is equals to 0, right. So, I can write E is equals to minus V2 cross B. Let us take the curl of this as this minus V2 cross B cross B. Okay. Now, so we have a vector triple product which is like A cross B cross C, which is to be written as B times C dot A minus A times C dot B. So, using this I will write E cross B as equal to minus E cross B is equals to V 2 B square minus B times V 2 dot B, right. Now, this is a very peculiar part. So, let us say before I analyze this, I will tell you what I am trying to do again. What I am trying to do is, I have these three differential equations, let us say these three second order differential equations, d square Vx, d square Vy, and we already have a solution Vz, right. The solutions of d square Vx and d square Vy are going to be Vx and Vy. What is the origin of this? What is the origin of this second order differential equation? The origin of this second order differential equation is simply this, equation number 1, right. So, origin of this second order differential equation is simply the force expressed in terms of electric and the magnetic components, right. Now, starting from here, I have been able to obtain two second order differential equations, d square Vy by dt square and d square Vx by dt square. So, the solution of these two differential equations has to tell me how the particle's velocity will change with respect to time when you have electric and magnetic fields. Okay. Now, I have been able to solve these equations to get the solutions as this, Vx is equals to this and Vy is equals to this plus this. So, what I realized is that Vz, of course, the z component of velocity is changing linearly with respect to time plus a constant value. That means, this is the initial value with which the velocity with which the particle has started, or when the particle starts to experience the magnetic field and electric field, this is what the velocity to begin with. So, in addition to this, the velocity at any instant of time. So, Vz at any instant of time is this plus a linear component which is changing with respect to time, right, fine. So, Vz is clearly defined, there is no ambiguity in Vz. But what is Vx and Vy doing? So, Vx and Vy, when I get the detailed solution, you can try yourself by substituting this, taking the second order differential equation, second order derivatives and substituting this into these two equations, you can see for yourself whether these equations satisfy or not. In any case, what these equations represent is that Vx and Vy have terms which are indicating circular motion. That means, the circular Lamar's precession of the particle is preserved. So, in addition to this, you have another term which is also velocity, by the way, right. So, B is E by C. So, that is still the velocity. So, now in order to obtain the explicit nature of this second term, we go back to the original equation we started from. The original equation, the solution of the original equation is generally in two terms, which are V1 and V2. V1 is the term which indicates time dependence and V2 is the term which is constant in time. So, we have the same thing, we have time dependent terms and we have a constant term, right. So, just to get that, what I have done is that I have taken a cross product of this, and now by resolving it, what we have seen is that, okay. Now, if you look at this, so E is in one direction, the electric field is in one direction, the magnetic field is in another direction, let us say, right. Now, here E cross B is a vector, this is a vector, right. Now, what you see is that this, the right hand side, the second term on the right hand side, V 2 dot B is a scalar, right, is a scalar, and this is a vector, fine. Now, what I understand is that, so this term scalar multiplied with a vector will still be a vector in the same direction. So, the scalar multiplication is not going to change the direction of the vector, right. Now, E cross B is in a particular direction and this B multiplied. So, this is not the cross product that I am trying to write here, let us say B dot or not dot B multiplied. So, the scalar, its magnitude will change, but its direction will not change. So, this will be in a direction which is not in the direction of E cross B. So, this vector, let us say, let us call this vector as F, this vector F will be in such a direction which is perpendicular to E as well as B, right. That means that it will not be in the direction of B, certainly not in the direction of B. So, when you are talking about the direction of E cross B and the vectors in the direction of E cross B, this term can be neglected, need not be considered. Okay. Now, what does it mean? It means that, so if you simply write, so E cross B is equals to V2 B square minus B into V2 dot B. So, this term gets neglected and we will write V2 is equals to E cross B by B square. Okay. So, this is called as the drift velocity. Or drift of the guiding centers. Now, whenever there is a charge particle movement in the presence of an electric field, we call the velocity that is attributed to the particle as the drift velocity. So, this is the drift velocity that is attributed to the guiding center. Now, one very particular thing about this is that, so there is no dependence of time in this. So, we have taken electric and magnetic field to be static in nature, right. So, that means that there is no time dependence in this solution, and V2, the most important thing is V2 does not depend on Q and does not depend on the mass. So, the velocity, the drift velocity that is attributed to the particle, the guiding center of this motion, neither depends on the charge nor does it depend on the mass. But unlike in the electric field or in the magnetic fields, in the electric field, let us say the electric field is, if it is along the z axis, we have seen that most of the cases when it allows charged particles to be experienced, then there will be a polarity, and depending on the polarity, charge separation will take place and a secondary electric field will be set up. And in the magnetic field, the polarity was in terms of the charge again. The positive charged particles were gyrating to the right and the negatively charged particles were gyrating to the left. So, the field was specific to the polarity of the charge. It is not that all the particles were experiencing the same effects. No, the field was specific or biased to the polarity of the charge. Now, in this case, it is not like that. In this case, it is the velocity, that is the drift velocity is independent of the charge and mass of the particle. Okay. So, this was something about the charged particle movement in the presence of electric and magnetic fields. Okay. So, in the discussions ahead, what we will see, we will try to draw trajectories for the particles movement in these different types of fields, and we will try to explore more on these topics. Okay. Thank you.